Hello and welcome to another Introduction to Astronomy lecture. This is lecture number 17 on neutron stars and black holes, two of the coolest things in the entire universe, in my opinion. In today's lecture, we will learn about neutron stars and their spinning brethren, the pulsars. We will also learn about white dwarf nova and how those are related to Type 1a supernova. We will talk about how sometimes neutron stars merge, and that can then lead to the creation of black holes themselves. We'll also talk about the different types of black holes. There are classical, and then there's relativistic, which involves Einstein's theory of general relativity. There's also, when we talk about black holes, we have to talk about the singularity and the event horizon that is around the singularity. And then lastly, we'll talk about how we discovered black holes and how we know that they are real physical things in our universe. So, when really massive stars, much more massive than our sun, reach the end of their life cycles because they run out of their nuclear fuel, there's two possible outcomes. You can either become a neutron star if it doesn't have quite enough mass, or it can become a black hole if it's massive enough. That exact cutoff isn't quite known. So neutron stars are some of the densest, or actually the densest objects in the universe, where the force of gravity is nearly 10 to the 11 times greater than that on Earth. So that is, I think, 100 billion times greater. I think that's what 10 to the 11 is, 100 billion. And the mass or the neutron star is composed of 95% degenerate neutrons. You can almost think of neutrons as being giant atomic nuclei since they are made up of so many neutrons. They have nearly 10 to the 57 times the mass of a proton and the diameter of a small town, about 20 kilometers. So I often see little science like images and like the news or whatever when they're talking about neutron stars, and they always love putting a neutron star over like San Francisco or New York in their little graphics. And so you can think of neutron stars as having similar sizes to small towns or little like dense city areas. And despite their small size, they are still capable of signaling their presence across huge distances in space. We will see that neutron stars sometimes can be very bright radio sources. So now we're going to learn about a hero of mine. In 1967, while studying distant radio signals, the PhD student Jocelyn Bell observed what she described as a bit of scruff, a strange radio signal that had never been seen previously. We can see her on the left in front of the radio telescope that she was using to study the sky, and then we can see her recorded data. And you can see the pulsar is indicated in the center as CP 1919. And you can see there's a little bit of interference next to that, but it's really cool. This is a PhD student, Jocelyn Bell, who discovered this. So her discovery in the constellation of Vulpecula, which is in the southern hemisphere, was a rapid and sharp oscillating pulsation of radio waves that arrived every 1.33728 seconds. It had a very predictable signal. Jokingly, it was postulated that this was a sign of life, that somebody was broadcasting out into the universe, and so this signal was jokingly called the Little Green Men signal. But after more searches of the sky were done, more similar signals were found, and it was then realized that these were very unlikely to be from a civilization, but were likely some source of natural radio waves. And so today we now know that there are over 2,000 of these pulsars in the sky, and that stands for pulsating radio source. So Jocelyn Bell unfortunately did not receive the Nobel Prize for her discovery. Her PhD advisor did. So we celebrate her because she was robbed of her rightful award in Nobel history, but in my heart, she is the epitome of astronomer, a student who is working as hard as she can and makes a discovery. That is the essence of an astronomer, and she's a hero of mine. So now let's talk about pulsars, those pulsating radio sources. So they are spinning neutron stars that are sending out little beams of intense radiation along their poles. And so since they're spinning really rapidly, sometimes those beams line up with the Earth. And so as it spins, it kind of looks like something pulsing on and off. They spin really fast with periods of anywhere between 1/1000th of a second to about 10 seconds. And so, while their origins were once mysterious, we now know a lot more about them. In 1968, a pulsar was found in the center of the Crab Nebula, which we can see being shown on the right in different wavelengths. And so this is a gaseous nebula that was produced by the supernova SN 1054, which corresponded to a supernova that was historically recorded by Chinese astronomers in the year 1054 AD. So we knew when that star exploded, and then we're able to do some backwards physics work to understand what happened. And so the discovery of this pulsar amidst the supernova remnant, where a neutron star was expected, immediately hinted at the origins of these pulsating signals as being from a neutron star in this nebula. And by combination of both theory and observations, astronomers will conclude that pulsars were indeed spinning neutron stars. So you can picture them kind of like cosmic lighthouses, where they've got these two beams spinning around. So the rapid angular momentum of the neutron star sweeps the north and south poles of the magnetic field around, and there's synchrotron radiation accreting along the poles, and this allows charged particles to collide with the star's surface, and that gives off a lot of heat and radiation in the form of radio waves. So there are actually quite a few pulsars in our Milky Way. They have a lifespan of about 10 million years before they no longer have enough angular momentum to continue radiating out. And there's a new one made about every 25 to 100 years in our galaxy. So the Crab pulsar is pretty young, given that it exploded in 1054. It's less than 1,000 years old currently, and it has a very short period because it's still spinning very fast. But older pulsars slow down, and so they have much longer periods. These ages can be determined since since older pulsars generally radiate longer radio wavelengths. That's a tongue twister. Well, the younger pulsars often have pulses that are in the X-ray, UV, and visible as well as the radio. So by using this lighthouse model, astronomers note that they are only able to observe pulsars that radiate along the line of sight. So that means that there are probably many, many more pulsars in our galaxy that we just can't observe because their beams of light will never strike the Earth because of how they're spinning. Surprisingly, most pulsars are not in the center of gaseous nebula, though they are all spinning neutron stars. This is twofold since the lifetime of a spinning pulsar is nearly 1,000 times greater than the lifetime of a remnant nebula. And so some neutron stars have been kicked out of their nebula at birth due to type 2 supernova. So now we're going to talk about another end stage stellar form, and this is the white dwarf. We've talked about white dwarfs a bit before, but now we're going to talk about how they sometimes go nova. So previously, many of the supernova that we've talked about have been from only one massive star. But many of the stars in our galaxy and in the universe in general are in binary systems. As many as half of the stars are in binary systems. So it's pretty intuitive to then assume that multiple stars in a binary system will influence that stellar evolution. So now let's consider a binary system where there's one low-mass white dwarf and another main sequence star. That main sequence star is going to substantially lose mass to the white dwarf from its solar winds. As fresh hydrogen from the outer layers of that main sequence star accumulate on the surface of the white dwarf, it is then heated. And that white dwarf develops an outer layer that can do hydrogen fusion, and it does it extremely rapidly. This burst of fusion tears away much of the newly accumulated material, and this suddenly increases the white dwarf's luminosity. This is what we call a nova. This nova generally does not disrupt the electron degeneracy as long as the accumulated mass has still remained below the Chandrasekhar limit. So we talked about white dwarf nova, but that was in the situation where the accumulated mass remained under the Chandrasekhar limit. But sometimes it will accumulate over the Chandrasekhar limit, and then electron degeneracy cannot stabilize the collapse. And this gives us our type 1a supernova, which are incredibly important for astronomy and for our cosmic distance ladder, if you remember. So as the white dwarf accumulates matter, the core is heated, and this allows for new nuclear reactions. And this white dwarf simmers, it boils for nearly a century with this heat. And the temperatures builds until suddenly a rapid, enormous blast of fusion can occur. And this is primarily carbon fusion, which takes place inside the white dwarf. And this actually explodes the white dwarf. It literally blows it apart from the inside. It is blasted apart, leaving nothing behind. These explosions of a white dwarf in a binary system are referred to as a type 1a supernova. Type 1a refer to a lack of hydrogen and an abundance of silicon due to the carbon fusion reaction. Unlike type 2 supernova, type 1a supernova leave no remnant behind. The white dwarf is completely destroyed. But type 1a supernova are unique because they occur at a once relatively constant luminosity. So knowing that luminosity means that you can really make accurate distant measurements to it because you will know what its absolute magnitude would have been, and then you can use its apparent magnitude and do the distance modulus. Alternatively, there has been some evidence for type 1a supernova that may occur when two white dwarfs merge and their combined mass is greater than the Chandrasekhar limit. Still, in that scenario, no remnant remains afterwards when they merge and explode. We can also have neutron star mergers. These are much rarer given that neutron stars are themselves rather rare, so the situation where two of them collide is even more rare. However, it does and has occurred. So, uh, in type 2 supernova cases, a main sequence star will share a system with a neutron star. And if the material transfers between the two and is pulled into the neutron star, the material compresses, heats, and explodes in that burst of fusion. But if the positioning of the neutron star with respect to the inward falling material is just right, that neutron star will begin to spin faster. That will give it a rate of up to 500 rotations per second in what we call millisecond pulsars. And that's just one type of neutron star interaction, but the other is when two neutron stars merge. Neutron stars occasionally collide with each other, and when they do, this gives off a huge amount of energy, and so much so that it actually disrupts space-time itself and sends out gravitational waves, which can be detected by the LIGO experiment. And they first successfully detected gravitational waves from a neutron star merger in August 17th, 2017. But now let's talk about the true oddballs of space that everyone knows from science fiction and now from reality. Let's talk about those black holes. So, when even more massive stars than those that created neutron stars die, they leave behind, or they create the conditions where not even neutron degeneracy is strong enough to stop the collapse of the core. This is when the core itself is greater than 3 solar masses. There is no known force of nature which can stop this inwards fall of gravity in these massive stars. And so all of the matter and mass is crushed into an infinitely small space and volume. That infinitely small point is what we call the singularity. And that is what the black hole really falls into. The hole in space leads down to the singularity. So the first person to really understand black holes and include them in his theory was Albert Einstein in 1916 with his theory of general relativity. And now we have a little aside that from the first observations of Galileo to the introduction of the formulas from Kepler and Newton, astronomy has always been a study of how things are interacting gravitationally. And it wasn't until 1916, with the development of general relativity, that we could really see what gravity does. Rather than just make things fall down, we could kind of create a mathematical framework. But even then, we have a framework for how it acts, but we don't know what exactly it is. Every other force that we know of acts by exchanging particles. However, gravity, which we know is a force, we haven't discovered the particle that is responsible for gravity. The thing that fits best with gravity is Einstein's theory of general relativity, in which gravity is a consequence of mass curving spacetime. So if you can figure out how to include gravity in particle physics, you will be one of the greatest scientists ever. You will have your name included with Galileo, Kepler, Newton, and Einstein. So now let's talk about the classical black hole and how that's different from the relativistic black hole, which we'll talk about in the next slide. So in a classical collapse, the core of the collapsing star just keeps shrinking down from about the size of the Earth to 20 kilometers in about a quarter of a second. This results in escape velocities nearly half the speed of light, until neutron degeneracy pressure can no longer stop the collapse as well. And as the core continues to collapse, the escape velocity then continues to rise, and it actually exceeds the speed of light, which means that essentially not even light can escape from the gravitational force of this black hole. And so this creates a black hole which emits no light, and anything falling into it can never return. This is our classical uh, model of a black hole. But we now know that Einstein's theory of relativity allows us to treat gravity as a curvature of spacetime. His theory of relativity is one of the most rigorously tested theories ever, and it still holds up. Einstein has always won out so far whenever we try to challenge him. So it really seems like this is one of the most accurate pictures to describe our universe. So as gravity increases, the curvature of space-time gets larger as well. So you can imagine like a sheet of fabric in which something heavy is just pulling down and creating a very, very deep hole within the fabric, whereas everything else around it is still relatively flat. So for example, if our sun could shrink down to the size of 6 kilometers, only the light emitting perpendicular to the surface could escape. And if it was shrunk even more, then there would be a limit in which all of the perpendicular beams could no longer escape. So if we look over on our graphic on the right, the one labeled 11, we can see a guy standing on the surface of the sun with like a flashlight out, and we can see on the left all of the beams are escaping in the original scenario, the one labeled A. But in B, where we have a smaller radii of the star, so a stronger force of gravity, we can see that Unless it is straight perpendicular off the surface, the paths of the light curve back around and end up on the surface of the star. And so essentially all radiation travels through this space-time, and as gravity increases, it is no longer possible for that light to travel out in a straight path. All light actually travels along a curved path which would lead back inwards in a black hole. And so for a collapsing star in this black hole, out has no geometric meaning, and the star becomes trapped in its own pocket of space-time, curving back in on itself so that there is really no outwards escape. Every line leads back to its same starting position in a black hole. So what happens inside the black hole is still a little bit of a mystery, but we can really see what's happening outside the black hole pretty clearly up until a point. So that point is called the event horizon, and it is the boundary in which a black hole cuts off communication from the outside universe. It is also the distance at which the escape velocity is then equal to the speed of light. So all objects that sink below the event horizon can no longer be seen from the outside because space-time has curved inwards. So these characteristics were first postulated by Carl Schwarzschild or Schwarzschild. I believe it's Schwarzschild, if you're being particularly Germanic in your pronunciation. And he was able to calculate the radius of an event horizon. And it's actually really only dependent on the mass of the singularity. And so this is called the Schwarzschild radius, named after him. The Schwarzschild radius is really the boundary of a black hole, and it only depends on the mass of the inner material. But in general, there's not a whole lot of change to the Schwarzschild radius. So if the Milky Way itself were a black hole, its Schwarzschild radius would be 1,012 kilometers. If the Sun were a black hole, its Schwarzschild radius would be 3 kilometers. And if the Earth were a black hole, its Schwarzschild radius would be 1 centimeter. So those are all the radii that you would have to compress all of that matter down to create a black hole. So if you wanted to make the Earth a black hole, if you were a sci-fi or a comic book villain, then you would need to compress the Earth down to 1 centimeter for gravity to then take over and make it a black hole. So in fact, the gravitational field outside the Schwarzschild radius is no greater than the gravity of the original star. And this contradicts the fantastical myth that a black hole could swallow all mass in the universe. Black holes are not going to suck down all of the matter around them. Only the stuff that is orbiting around them that slowly loses angular momentum and passes through the event horizon actually gets swallowed by a black hole. So now let's talk about the center. We're gonna have to really stretch our imagination, and that's fitting since we are being stretched by the black hole. So there's this famous saying, it's actually a theorem, that black holes have no hairs because nothing sticks out of them beyond the event horizon. It would essentially be like a bald person. It's just a smooth radii in which nothing is coming out. And then once you make it past that, you're in the black hole forever. And so at the center of the event horizon, where all matter continues down to collapse into a point of infinite density, is the singularity. But all laws of physics break down at the singularity. So you can kind of think of black holes as like hiding breakages in the laws of physics. Black holes are like cosmic censorship in that way. Our laws of physics aren't quite working, so the universe is like, oh, just sweep that under the rug. No one look. But what would happen if you were approaching a black hole? So as you approach the event horizon, the curvature of space time would make space and time actually behave differently. Just outside the event horizon, any signal sent would appear much longer and widely spaced until it approached infinity. This would make it appear to the outside as though you are frozen in time. So if you fell into a black hole, what an outside observer would see is like a picture of you that is slowly getting redder and redder until it no longer is a wavelength that you can see. Yeah, so this is weird stuff. So all matter falling into the black hole appears from the outside to stop at the event horizon, where it is frozen in place and then takes an infinite amount of time to fall through. But this matter beyond the event horizon cannot be seen due to the curvature of spacetime. So from your reference frame as you are falling into the black hole, time is still going normally for you as you fall right towards the singularity. But there is no turning back, as all signal has been lost from the outside universe, and spacetime only points inwards towards the singularity. And as this is happening, something really weird begins to happen to the matter in your body. It gets elongated. The pull of gravity at your feet would actually be greater than the pull of gravity on your head. And so you would start to be stretched out infinitely long. And this is where scientists get really funny with the names. They call this stretching out spaghettification, like you are being turned into a very long, thin strand of spaghetti. All right, so black holes, they are basically cosmic censorship, where once something has made it past the event horizon, it can no longer be observed or make contact with the outside universe. So, how do you detect a black hole? How do you see a black hole? Well, the trick is that you can't really look for a black hole itself, but you look for its influence. So in a multi-star system, if one very massive star collapses into a black hole, but its companion survives, then we'll see that one of these stars has sort of disappeared. So the black hole disappears from the view of its gravity from view, but its gravity remains. So the light is gone, but the system is still behaving similarly gravitationally, which implies that there is now an invisible component. So astronomers often, when they're searching for black holes that are in binaries, these are stellar mass black holes, they are looking for stars whose motion appears to be in a multi-star system, but that it is alone, or appears to be alone. It has an invisible black hole partner. But invisible is not enough, since faint stars, dwarfs, and even neutron stars are possible. Astronomers must confirm that the invisible member of the multi-star system has a mass greater than 3 times that of the Sun to confirm that it is a black hole candidate. So we can see an example of a black hole, Cygnus X1. This was the first confirmed black hole ever discovered, and it is orbiting a massive star, much more massive than our own sun. And so this black hole has a mass of about 21 times the mass of the sun, and its companion is 40 times the mass of our sun. But as the old saying goes, seeing is believing. So how can we see a black hole? How can we nearly directly detect radiation from around it rather than its gravitational influence on a nearby star? So visible stars radiate and eject stellar material, which can fall towards that mutually revolving invisible companion. That infalling matter will form an accretion disk around the black hole. And these accretion disks are very violent and very hot and chaotic, and so they can reach temperatures of up to 100 million Kelvin, which allows them to emit X-ray radiation. So we know that young neutron stars can also emit X-ray radiation, so careful analysis must be done when looking for X-ray sources as black holes. So we have actually managed to image a black hole in the past few years. So X-rays have long been quintessential for locating black holes, but X-ray astronomy is very difficult because it has to be done out in space. X-rays do not survive the trip through Earth's atmosphere, and so we need space telescopes for that. After the launch of the first sophisticated X-ray telescope in the 70s, we were they had resolutions capable of finding the precise locations of X-ray sources, and so astronomers have been able to find lots of binary systems that have matched up with black hole candidates. The first that was discovered was in 1964, Cygnus X1, and this was a black hole in a binary system with a visible supergiant O-type star. So that would be a massive blue star. And this showed measurable X-ray flickering, which is indicative of an invisible companion that has about 15 times the mass of our sun. This immediately tells astronomers that the visible companion would be far too large, or that the invisible companion is far too massive to be a white dwarf or neutron star. If it has 15 times the mass of our sun, it could only be a black hole. And over the past few decades, more and more observations have been made with the Hubble Space Telescope, the Chandra X-ray telescope, LIGO and Virgo, which actually measures the gravitational waves. And we've actually been able to take physical pictures with radio telescopes of the event horizons. This is known as the Event Horizon Telescope Array. So by combining the radio telescopes around the world, we can actually make, in a sense, a radio dish the size of Earth itself. And so this allowed astronomers to take an incredibly detailed image of the X-ray or of the gases swirling around the black hole in the center of our galaxy and in the galaxy. Oh, I can't remember. I think it's M78. Um, but they were actually able to take pictures of the gas swirling around the black hole, and they were able to get a picture of the black hole's shadow. So that orangish, reddish, yellow donut that you see is actually a picture of the gas surrounding a black hole. That dark shadow in the center is where the black hole is. So we can't see the stuff that is directly behind it. And so that's why it gives us this shadow. And you may see that there's some little swirl lines in there as well. That is from the polarization of the light. So we can tell that that material is swirling and spinning around that black hole as it falls towards its event horizon. It's really, really incredible that something that was just a theory like 50 to 100 years ago is now something that we can take pictures of using telescopes that are essentially the size of the planet. That's just incredible. It's truly incredible. And I hope you're all just as awestruck as I am that we are able to take pictures of the craziest thing in our universe, a black hole. This is the end of our lecture on neutron stars and black holes.